So, let us start this lecture with a thought process. The meeting of two personalities is like the contact of two chemical substances. If there is any reaction, both are transformed, right? Yes or no? So, that is also a similar thing to what is happening. It is told by the C.J. Jung. And let us recall that we discuss about elementary reactions and also why the single step chemistry is not mimicking the nature, right. And then we looked at basically how to write the reaction, particularly for multi-step chemistry, in a compact way, and so also the reaction rate. And towards the end, I also discuss about there is a need for to find out the expression for the reaction rate coefficient or specific reaction rate, and invoking the collision theory, right. Collision theory means basically there will be collisions between the what we call molecules and atoms, right, that, right, which will be moving randomly. And when it is moving randomly, then we will have to look at the kinetic theory of an ideal gas. Keep in mind that we are keeping the ideal gas in our mind. Why? Because ideal gas can be used very easily for combustion problem, being at higher temperature and moderate pressure, right. So, let us look at, we will take a cube, right, where the these particles are moving randomly. It is moving here and there, they will be colliding each other, right. And for that we will make some assumption what is happening, and that is basically assumption for the kinetic theory of gases. So, what we are assuming that this container or any cube or something we are considering, which may be any shape, but we are taking a cuboid. It contains a large number of molecules with spherical shape whose size and mass are identical, right, but they vary from gas to gas. Keep in mind these are assumptions, right, need not to be same, right, spherical size, because you have seen the molecules are various shapes and depending on what it is, but we are considering for the simplicity. And total volume of all individual gas molecule is negligibly small as compared to the volume of the container. This is assumption we have discussed earlier for an ideal gas. And when this is moving, there will be some separation distance between the gas, right. It is not that all are compact like a solid or in a liquid, right. So, these are moving. So, there is a separation distance. The average separating distance between gas particles is quite large. That means, one particle is here, another particle will be somewhere else, right. So, as a result, the force of attraction and repulsion between molecules is negligible, right. There is not much this thing. And these molecules with higher kinetic energy, right, will be moving around, right, and colliding with others, right, and it will be moving with a very high velocity, right. And whenever there is a collision taking place, that will be elastic in nature. What does it mean? Either they are colliding each other or they are colliding with the wall, that will be elastic in nature. That means there won't be any change in the kinetic energy, or the velocity with which it will be colliding, it will be not reduced, but that is not the case, it will be reduced, right, we have seen. And as it is moving in the randomly, it is very difficult to handle. Why? Because if I will track one molecule, talk about velocity and then about momentum, about all the forces acting, and then doing solving, even it will be small volume of 1 centimeter cube, if I will consider, it is very difficult to handle that, even using the best supercomputer available in the world at this moment. Are you getting? So, therefore, we will have to do that thing in a statistical way, that means average way, right. and treatment can be possible only when the large number of molecules is like number of molecules involved is quite large and kind of thing. And interaction, I cannot take a few molecules and then consider, okay, this is the statistical, then statistics having no meaning, right. Therefore, large number of molecules will be there. But whereas if I go to the other one, actual simulation, lesser the number of molecules, better it will be because I can, my situation or handling will be easier. The interaction among the molecules are negligibly small except during the collision. When it is colliding, because there is no forces of attractions and repulsion, therefore, when it is not colliding, you do not have much thing in that. And mean free path is quite large as compared to the molecular size, right. Mean free path means the distance between two collision basically is the mean free path. And pressure applied on the walls of the container is due to collision of gas molecule with the container, not any other effect. Okay. The molecules of gas moves with the different velocities, right, and different kinetic energies, and of course, you can consider that it will be different molecular weight, mass will be also different, but we will not be consider that thing. As you go along, we will see, we will be considering a mass, mass remains, mass is same for all molecules, we will start, then we will have to do that. Kinetic energy of gas molecule depends on the temperature of the gas, right, because the higher the temperature, the kinetic energy will be higher, because the molecule will be moving at a faster velocity or the speed. So, what we will do? We will now basically invoke this kinetic theory of gases from the very simple things what you might have studied in your class 2, but you might have forgotten by this time. So, we will recall it and then do that. Okay. So, let us consider a Q here, right, and let us say this is having x direction and this is having y direction, this is having z direction. Okay. Let us say there is a, I mean we are considering starting with a one particle, right, kind of things, and then we will move into that other one. Let us say there is a particle here, right, which is moving with a velocity Vx, and it will move. What will happen? It will go and hit the wall. This is your wall, right. And it will go and hit, and then it will come hit this thing. What will happen? Elastic collision. That means it will be coming, and this is having mass m. This particle is having mass m. So, therefore, what happens? This will be coming with the velocity Vx, mass is same m, right, because of elastic collision. Now, I want to find out what will be the pressure of an ideal gas, because we are considering ideal gas, right. Now, as collision is perfectly elastic, therefore, Vx in the what you call positive x direction is same as when it will be just returning back with the same velocity, right. So, therefore, change in momentum of this molecule, right, in x direction, what it would be? Mass is not changing, mass is same, okay. M final minus initial, right. What is final? Final is what it would be? Minus Vx minus initial will be minus Vx, that is 2 m Vx, right. But there is a conservation of momentum. So, therefore, the momentum, change in momentum are imparted to the wall, right, is equal to 2 mvx, just negative sign like will go away. Now, if you look at, I want to find out, let us say total number of collision which will be taking place on this wall, right, because my interest is to find out pressure, right. Pressure is basically force upon area. So, for force I want to find out, I will have to find out rate of change of momentum, right, and by the all the particles. And if it is all the particle, let us take that there are let n be the number of identical gas particles, I can say molecules, okay, particles per unit volume. What is this n? That means n is basically number density, right, is not it? It will be number density. That is nothing but n naught by V. What is n naught? Number of particles or molecules, whatever you call, right. I can say molecule because I will be using molecules later on, okay. And V is the volume. Now, I want to find out, and keep in mind that this is occurring in a very small interval of time delta t, okay, because this when is colliding is the time is very small, it is a go and collide very fraction, very small time scale, right. During this small time, right, during delta t, right, number of collision right with velocity Vx, right, collisions of molecules, right. I am using particle molecules in a interchangeable, okay. With Vx, right, what it would be? What it would be? How many number of collision is taking place. If you look at what it would be, number of collision means number of particles will be there, like that many collision will be taking place, is it so? That means, can I write down here number of collision means basically n into V, is it right? That is not right, because we are considering this will go and again go back and hit and come back. So, this will be half, yes or no? It will hit, it will come back and hit this wall, this is also wall. If I am considering along with x direction only, that means it will come and hit other wall also, yes or no? That means this will be divided by 2. Is that clear? No? Because the particle is going and coming, then it is going and hit here and again it will come back. So, therefore, half, right. So, now what is this volume then? Because I need to calculate this volume. What will be this volume? Volume will be Vx, right, with the velocity which is moving into area, if I consider this is my area, right, okay, into delta t into area, because Vx is meter per second, this delta t, during that delta t it is occurring. So, this is the V. So, therefore, total momentum transfer to the wall by all the molecules, what it would be? We know the momentum transfer to the wall, right, by the single particle or single molecule, what is that? 2 mVx, into what? Into will be number of particles, right, isn't it? Yes or no? That means n v by 2, n, and v is v x delta t area divided by 2 to cancel it out. So, I will get n m v x square, right, delta t into a, right, yes or no? So, now I will have to find out total momentum, then what will be the rate of change of momentum will be divided by delta t, and what will be pressure? I will write down pressure will be rate of change of momentum, right, that is, right, okay, let me write down rate of change of momentum divided by area. So, that will be, this is your total momentum change, that means what is the rate of momentum, rate of change of momentum, that is, okay, let me write down here, because rate of change of momentum is nothing but n m b x square delta t a divided by delta t, right, because this is change in momentum, right. This will cancel it out, I will get n m v x square area, right, and this is, then I will write down n m v x square area divided by area, cancel it out, and there will be also what you call n m v x square, right. And keep in mind that this is about only one single these things, right. There might be, is not that particle or the molecule will go and hit the wall in the x direction, right. Is it possible? It is not possible. So, the total velocity, if I take in a write down vectorial form, will be v x, if I say this is I and then v y j plus v z k, because all three direction it can happen. But if I consider this to be isotropic, that means for isotropic case, situation, right, v x is equal to v y is equal to v z, right, okay. Are you getting? Now, keep in mind that we are looking at statistically, therefore, there will be some average also, right. So, I can write down v x average square is equal to v y average, because there are several number of particles are there, it is not a single particle, there will be n number of particles. So, therefore, you need to look at average velocity, right, average velocity, right, and is equal to v z average square, because this is average velocity, right, along x direction, that is v x square, and is equal to, I can write down as 3 v x square average plus v y square average plus v z square average, right. I can is equal to z square average, I am just representing, right, 1 by 3 I can write down, because if I say this is v, that means keep in mind that this is basically average over the things, right, this I can say, right, because of fact that there are several number of molecules are there, therefore, we need to consider average velocity. So, therefore, I can write down P, if I say this is equation 1, then equation 1 for becomes P, I can say this is what you call P is equal to 1 by 3 n m v dash average square, right. is for the all the molecules what we are considering. That might be thousands of molecules, okay, but that average velocity we are talking about, right. Now, you might be wondering why we are doing that, why we will be looking at pressure when you talk about what you call collision theory and other things, but we will see that we will be more interested to look at the pressure is also important, and also the we will have to look at what will be the average velocity, right, of the molecules or the average speed of the molecules. So, let us look at that. If you look at, we have seen that P we have seen that is 1 by 3 n m v average square, right. If I say this is P v, P v means is a what you call volume, this is the V is volume. Keep in mind that I am using V for velocity and V for volume, okay, is equal to 1 by 3 n m v square into V. I can write down V here. Yes, yes and no. Now, what is this NV? NV is nothing but your N naught is equal to NV. So, I can write down 1 by 3 N naught, right, mv square divided by 2 into 2. I can write down 2 here. And what is this one? This is basically translational velocity or the kinetic energy of the molecules, which is due to the motion. What you call this? This we call it as a internal energy. Can you call it? Because the molecules are there, it is going and heating, right. Of course, there might be a molecule which will be vibrating, right, and there will be also rotational, but you are considering the single, and then this will be, we call it as a internal energy due to translation, okay. That means this is basically 2 by 3. By that I can write down that PV is equal to 2 by 3 U. Can I write down? 2 by 3 U. U is the internal energy due to translation, translational motion. That means, okay, we know from for ideal gas law, right, for ideal gas law, PV is equal to 2 by 3 U is equal to N R U T. Yes or no? Right? And I can write down this thing is basically we know this thing, right. I can write down basically U is equal to 3 by 2 N R U T, and what is this U? U is equal to N naught M V square by 2, right, that is nothing but U is equal to 3 by 2 N R U T. So, this will cancel it out. So, therefore, what will be 3 N R U T, right, divided by N M, right, N naught, yes, you are right, N naught. Now, what is N? N we know it will be N naught divided by A V. What is A V? Avogadro's number, okay, Avogadro, this is M by molecular weight. So, this is Avogadro's number. Now, I will put this one here, that is 3 in place of n naught, right. Keep in mind what is this velocity? Yes, what is this velocity? This is basically velocity for molecule, right. This velocity is for a molecule, average velocity square. Why? Because I am dividing the n number of molecules, yes or no? N number is there, maybe some million molecules will be there, or maybe 10,000 molecules, whatever it may be, dividing. So, therefore, in place of n I am now writing n naught, right, divided by a v, and this is your R u t n naught m. So, these will cancel it out, right, v square. And what is this m and av? M, av is nothing but your molecular weight, right, yes or no? So, therefore, this velocity, if I take root, this became V RMS, root is equal to root. So, V RMS is equal to root over 3 RUT divided by molecular weight. Okay, make sense? And if you look at V RMS is proportional to what? Proportional to T half, and V RMS is inversely proportional to molecular weight by half. That means, if temperature is higher, that means temperature is higher, V RMS will be higher. If molecular weight will be lower, that means lighter molecules will have V RMS will be higher, yes or no? And keep in mind that molecular speed is independent of what? Pressure. Okay. So, we will stop over here and we will discuss in the next class, like what will be the, I will take an example, what is the velocity, what order velocity will be there. Will it be centimeter per second, meter per second, or something more? That we will see taking some small example. Okay, thank you very much.